comes out with me. Okay? Anyway, so the area of the nozzle, well, it's the ratio of the enthalpy difference. So if I take the isentropic enthalpy difference over the actual enthalpy difference, what am I going to get? I'm going to get a value that is greater than 1. So if I'm getting efficiency greater than 1, that doesn't make sense. So when you're solving problems, and you're going to end up doing this quite a bit in propulsion systems, that you want to make sure what is the numerator versus the denominator. And it makes sense, right? Because it has to be less than 1. It cannot be greater than 1. How can you get an efficiency greater than 1? So in this case, the actual, which is the delta from this point to this point, is smaller than the delta from this point to this point. So that's why it actually is in the numerator instead of denominator. Same principle, we applied it for, actually before we do that, well, what if I have a diffuser? You have some diffuser right here, you have some station 1 right here, some station 2 right here. What happens to pressure, velocity, pressure, velocity? I told you to use the garden hose as an example, so you already know what happens with a nozzle and subsonic flow. What happens for a diffuser? What is pressure upstream versus downstream? Which one is higher? So it's pressure versus velocity. Getting different answers. What happens to velocity?
Goes up.
Slows down. So velocity here is high, here is low. What happens to pressure? The opposite. Right? So it's going to go down, this is going to go up. So pressure goes up. So if I plot the same principle, the enthalpy versus entropy diagram here, and I want to keep it in the same page because I want you to see this as I'm doing it. So I got 2 pressure levels that I need to deal with. Which is the top and which is the bottom? I already said station 2 is the highest pressure. So what does this make? What does that do to this curve? Is that P1 or P2? P2. And what is this curve? P1, obviously. Okay. So starting from 1, right, which is going to start at a lower pressure. The isentropic process means delta S is equal to 0. So that means I have to walk vertically to 2. And this is 2 isentropic, 2s. Now the actual, what happens in the actual? Yeah, delta S is not equal to 0, so what I'm going to get is a curve that looks like this. 2 actual. So from that, these are your enthalpy differences. The equation is almost the same here. You just have to flip the subscripts. It's the same. Now, what is different here is the actual versus isentropic is what? High. So you actually, your efficiency for your nozzle, as for your diffuser, is equal to what? Enthalpy, 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 enthalpy. Minus, what are the subscripts? Is it isentropic versus actual, actual versus isentropic? Isentropic versus actual. Why? So isentropic versus actual. So 2s minus h1, 2 actual minus h1. So why is it that way? Well, besides greater than or less than, but from the physics standpoint, what are we trying to do with a diffuser? We're trying to expand the flow and get higher pressure through the diffuser. So by doing that, the ideal situation will be to expand it or get the higher pressure at very minimal energy possible, which is your isentropic process. Versus the actual, well, you end up putting in terms of flow work, in this case, which is enthalpy, more work to get to the same pressure level because of boundary layer effects, separations. What happens here is you get a boundary layer right here that thickens throughout. You get skin friction, which is, think of it as like drag. We're going to talk about it more as we progress through the semester. So that's why your ideal situation here is less energy to achieve the same pressure level than you were with a actual process. Does that make sense? You all agree? Yes. Okay. All right. So somebody's awake. Turbine. So let's take a turbine example here. So it's the same principle. What happens through the flow here? The pressure is really high here, and it's going to a lower pressure. So pressure is high going to a lower pressure. What is an example that we just did that's similar to this? Well, it's like a nozzle, right? The pressure is going from a high pressure to a lower pressure. Velocity is going up. So in this case, assuming the kinetic energy is actually very minimal, so I'm not counting for kinetic energy, I just want to look at primarily the pressure difference. So a turbine, what happens through a turbine, the flow expands across there and produces work. So accordingly, if I'm expanding, then I'm going from a high pressure to a low pressure. The isentropic process, meaning I don't have any losses inside, it's a 100% efficiency system, I'm going from 1 to the 2s isentropic process. However, that's not the case. You have turbine blades, you got boundary layers that are going on, you got tip separations inside. It's not a clean-cut flow path that you have in there. You have losses in terms of, think of it as a drag force. You have significant drag forces that are happening inside of the turbine blades that reduce the overall 100% efficiency that you have. So therefore, you end up with a non-ideal expansion. Ideally, I could get this much work, but I don't get this much work. I get only up to here. Does that make sense for the actual? Where did my other work go? Where is the difference between this one and this one went? Entropy loss. Does it make sense to people? Do we understand entropy? It's harder to visualize, but think of it this way. Ideal process, this is how I could take the heat engine that we talked about, T hot, right? And we had a heat engine. If I could take all my heat energy and transfer it to the heat engine and produce work, that's an isentropic process. But I don't get that. What I end up getting is, think of your car engine, you always get heat losses. It gets hot. It's supposed to be at the same temperature as you started that car engine, but it doesn't happen. It's just you can't control some of the entropy losses they have, no matter how much you insulate it. So you end up with heat loss. And by doing that, that's essentially the difference between the isentropic process and the actual process. And we outline work. Our work primarily is m dot. I have flow that is going through there. The enthalpy change, which is primarily your internal energy as well as your flow work. The enthalpy change multiplied by the mass gives me my overall work, and the efficiency is simply the actual process relative to the isentropic process. Does that make sense to everybody? We understand it very well. We're not going to get confused about this. All right, let's do a quick. What about compressor? Question. Oh, it's a good question, but most of the time, depending on what you're trying to do, you are changing internal energy. So think of what is internal energy. So we got a good question about internal energy. What is internal energy? Equal to C what? CV CV delta T. So if I have no temperature change or internal gas flow, then I have thing is, you always have that heat loss of some sort, and therefore your internal energy is always changing. So you might not have flow work, but you are changing internal energy. So think of it this way, that now we're getting into thermodynamics. I got a box, and I didn't insulate all the walls, for example. And I put a gas outside, it's 25C, and inside that gas is at 100C, for example. Flow is not moving. So i.e., what happens, flow is not moving in terms of enthalpy? Well, I have no PV. I have no flow work. Velocity is 0. There is no boundary work. There's nothing other than what's going to happen. Yeah, somebody's saying, yeah, heat transfer. So what's going to happen with heat transfer? I'm going to get the temperature here. What's going to happen to that temperature? It's going to decrease. So if it's going to decrease, what's going to happen to my flow energy? It's going to change. Make sense? Now, keep in mind that I'm assuming CV is actually constant as a function of temperature, and most likely, if you're not dealing with larger temperature gradients, you can consider CV constant. You're going to do in some problems with propulsion systems as we get to engines in general, you're going to realize I'm going to have you actually try the CV and CP as they're varying in temperature, but also you're going to fix it and you're going to realize how severe is that assumption and where is it valid and where is it not valid that I could take this. And this is, again, like I mentioned, essentially is if I have a large temperature gradient from 3000 in a combustor all the way to ambient temperature conditions, which is 300 Kelvin, well, that's a massive temperature gradient. I can't assume CP to be constant. I have to vary it. And gamma as well. You work with high-speed aero. We've always taken gamma 1.4. However, 1.4 changes quite a bit in the engine. That changes your thrust overall calculations. So I'll account for that. Let's do a compressor. I've got some input right here, some output right here, too. And I got some work out. So, in your notes right now, draw the enthalpy and entropy diagram for this. Work out, is it? We have to work in the compressor, by the way. So I most likely have two pressure levels. Which one is higher, which one is lower? Disregarding the work right now. What happens in a compressor? From the term compressor, it's compressing air. Therefore, the downstream pressure is higher. So my pressure here is higher than my pressure here. So P2 is right here, P1 is right here. So I'm starting from point 1. The isentropic process says what? Well, entropy, rate of change in entropy is 0, therefore I'm going to go with a vertical line. So that's your isentropic process. And the actual process is just going to be to the right. That's your actual process. Which in a sense you say, well, if you really want to compress the gas, the isentropic process is I'm going to put in this much energy, work-wise. This is my work input. Like what is work in here? Equal to